Hi, today we're going to look at Chapter 7, Section 4 in your chemistry book. This section deals with empirical formulas, finding empirical formulas from percent composition data, and also then using that to calculate molecular formulas. And so we're going to take a look at these two things here today. Um, the 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 empirical formula is defined as a formula that gives the lowest whole number ratio of each type of atom in a compound. Um, the empirical formula for ionic compounds is usually the formula unit. For molecular compounds, the empirical formula may or may not be the molecular formula, and we'll take a look later on at how you actually determine that. But first of all, we are going to calculate empirical formulas from percent composition data. And so let's take a look at an example of that. And we are given this data. Suppose a substance is found to contain 63.50% silver. We have 8.25% nitrogen and 28.25% oxygen. What is the empirical formula? All right, we're going to start by listing these elements across the top here. So we'll write silver, nitrogen, and oxygen. And then what we're going to do is we're going to assume that we have a 100-gram sample. And we do that because we're dealing with percentages here. So then each of these percentages becomes a gram amount of silver. And that's what we really need. We need the quantity, some kind of a quantity in grams. And so what this would do would be to give us a 63.50 grams of silver in our sample, 8.25 grams of nitrogen, and 28.25 grams of oxygen. All right, so in a 100-gram sample, that's what we would have. Now, we need to convert each of these to a molar amount. And if you remember, we can convert grams to moles by simply dividing by the molar mass. So the molar, if we divide each one of these by the molar mass of the element, for example, silver is 107.8682, and this is grams per mole. Nitrogen is 14.0067 grams per mole. And again, I'm getting these numbers from the periodic table. This is just the atomic mass, but it's expressed in grams per mole rather than atomic mass units. And of course, oxygen is 15.9994 grams per mole. So I divide each of those out, and I end up with the following numbers. You get 0.5887 moles of silver. We get 0.5887 moles of nitrogen. I'm sorry, 589 moles of nitrogen, and 1.766 moles of oxygen. All right, so now what we want to do is to calculate the mole ratio of this. And so look at those three numbers, and what we're going to do is we're going to divide each of them by the smallest. The smallest number is the 0.5887 moles, and so we'll divide each of these by 0.5887 moles. Okay, so we look at those original numbers, divide all three of these by that by the smallest number there, and that's going to give us this one, of course, is 1.000. This one, 1.00, and this one gives us 3.000. So if we look at those in terms of small whole numbers, we have 1, 1, and 3. Now these worked out really, really nicely. Normally you'll get numbers like 0.999 or something like that. Numbers very close to 1, or you might get 2.01, number really close to 2. So you may have to do a little bit of rounding on these numbers. But now these numbers will serve as the subscripts for each of those elements in the formula. So for AG, our subscript is 1. We don't write that. N, the subscript is 1. Again, we don't write that. And O, the subscript is 3. And we have AgNO3, or silver nitrate. And that's how we calculate the empirical formula, and that's what this is. It's an empirical formula. Now, it just so happens that that also is a formula unit of the ionic substance, silver nitrate. All right, let's take a look at a second example here. And for this one, we will use this problem. Determine the empirical formula of a compound found to contain 52.11% carbon, 13.14% hydrogen, and 34.75% oxygen. All right. Now, again, we start this one out the same way as we did the first one. We're going to list carbon, hydrogen, and oxygen across the top, and we'll put the gram amounts, we'll take the percentages of each and write that as a gram amount. So we have 52.11 grams of carbon, 13.14 grams of hydrogen, and 34.75 grams of oxygen. Okay, and now we're, again, to convert these to molar amounts, we have to divide each of these by the molar mass of the element. So carbon is 12.0107. It's grams per mole. Hydrogen is 1.00794 grams per mole, and oxygen is 15.9994 grams per mole. So when we do that dividing, we come up with 4.339 moles of carbon, 13.04 moles of hydrogen, and 2.172 moles of oxygen. Again, inspect those numbers and see which one is the smallest. And it's the 2.172, the oxygen. So we're going to divide each one of these by 2.172 moles, and that will give us our mole ratio. And of course, as we would expect, this one is going to give us 1.000. As we do the other divisions, we get 1.998 and 6.004. All right, and again, now in this case, the numbers didn't work out perfectly, but you can see that our mole ratio here, the whole numbers, that one is very close to 2. This one is very close to 6. And of course, that one is exactly 1. And so now we can write our formula here as C2H6O. That would be the formula, the empirical formula for that compound. All right, now let's take a look at how we can use this information to calculate a molecular formula. If you recall, we said that the molecular or the empirical formula may or may not be the molecular formula. What we can say is that the molecular formula will always be some number times some number x times the empirical formula. All right. So the molecular formula is always 1 times or 2 times or 3 times or 4 times. It's usually a fairly small number like that, times what we get for the empirical formula. So, and this then also tells us that that same number x is going to be equal to the empirical formula mass times the molecular formula mass. And this is how we actually collect or calculate this information. So we'll look at a problem that looks like this. A sample of a compound with a formula mass of 34.00 AMU is found to consist of 0.44 grams hydrogen and 6.92 grams of oxygen. Find its molecular formula. Okay, the first thing we need to do is go through our finding the empirical formula like we've done in the past. So we'll write our two elements here, hydrogen and oxygen. And now, because these were not given to us as percentages, but rather in gram amounts, we can just use those directly. So we'll just start with the gram amount. Remember when we were doing this where we were given percent composition, we assumed a 100 gram sample and we used that as the gram amount. But in this case, we just go directly to these gram amounts. So we have those two gram amounts. We're going to divide those by the molar mass. And when we get that, we got to be careful with sig figs here. We only have 2 sig figs in this one. And you can probably see already what's going to happen here. We're going to divide both of these by 0.433 because that is the smaller of these two numbers, although not by much. And to 2 significant figures, this comes out as 1.0, and of course this comes out as 1.00, so we have 1 and 1 for our small whole numbers. That means we get the formula H1O1, okay, or just HO. Now, if you actually try to construct that molecule, you can't. Oxygen has to form 2 bonds. Hydrogen forms 1. You can't satisfy all the atoms there by doing that. But this is our empirical formula. Now, the formula mass indicated by this formula then is, and we're just going to go through and calculate this the way we've done before. We have 1 hydrogen, 1 oxygen, and this is 1.00794. 15.9994. When we add those up, we come up with 17.0073. That's to the correct number of significant figures, AMU, atomic mass units. Okay, now we said earlier that X times the empirical formula mass is equal to the molecular formula. So some number X times 17.0073 is equal to 34.00. If you recall, that was the number that we were given up here in the problem as the formula mass of the compound. Okay, so now if we simply divide both sides here by 17.0073, we find that x is equal to 1.999 to 4 sig figs, and that is very nearly 2. So now we're going to use that x times the empirical formula is equal to the molecular formula. So we have 2 times HO is equal to H2O2. That, if you read your book carefully when we were doing oxidation numbers, you'll find that that is listed as one of the exceptions for the oxygen having the oxidation number of -2 in the case of a peroxide. Well, you feeling lucky, punk? Well, are ya? Go ahead, make my day.